Now we will see the effect of substituents on the acidic strength of aromatic carboxylic acids. Got it? We have already discussed the aliphatic carboxylic acids. Now we are going to discuss the effect of, that is, acidic strength on aromatic carboxylic acids. Now you see here, if you see this particular one, CH3COOH. So here the carbon atom is, what you can see is that sp3 hybridized. In the aliphatic carboxylic acid, the carbon atom is sp3 hybridized, which is attached to COH group. Fine. Now, in case of aromatic carboxylic acid, here the carbon atom is sp2 hybridized because it is alternately single and double bond. So here the carbon atom is sp2 hybridized. Look here carefully. The carbon atom here, this particular carbon, is sp2 hybridized. So sp2 means the what you can say, the percentage of S character is 33.33%, and here the percentage of S character is 25%. More is the S character, more is the electronegativity. More is the S character here, 33.33%, more is the electronegativity. So if I draw the structure here, you will find it out. If I draw the structure here, so this will exert minus I effect. That means the benzene ring will withdraw electrons from carbon, and carbon will withdraw electrons from oxygen, and oxygen will withdraw electron from hydrogen as a result. Got it? So due to this reason, the cleavage is going to take place easily, and hence H plus ion is readily released. H plus ion is readily released, so to say. Got it? Fine. This we come to know. If you compare the what you can say, alkyl group and the aryl group, we come to know that in case of aryl group, the carbon atom is sp2 hybridized. That means it is minus I effect. That means what? That means it more is the electronegativity. Alright, when it's sp2 means S character is more. S character is 33.33%. Here the S character is 25%. Alright. So more is the S character, more is the electronegativity. More is the electronegativity means definitely it will pull electrons from, that is, this carbon, and this carbon is going to pull from this oxygen, and as a result oxygen is going to pull from this hydrogen. Alright, and H plus ion will readily released. This we come to know if you compare the aryl and the what you can say, alkyl group, you come to know. But the cumulative effect is that, you know that COH group is also nothing but an electron withdrawing group. The cumulative effect is that it exerts plus I effect. Alright, it exerts plus I effect. And the plus I effect which is exerts, alright, the entire, that is aromatic acid, it exerts a plus I effect. The cumulative effect it is that. Got it? That is electron donating effect, not electron withdrawing, the electron donating effect. Alright. So cumulative means what? Because here not only minus I effect is there, plus R effect is also there, a resonance effect is also there. Because benzene ring also shows resonance, that is called the cumulative effect. Now, due to this cumulative effect, the aromatic ring attached to the carboxyl group has an overall plus I effect. Alright? Achha. But this plus I effect is weaker than plus I effect of the aliphatic carboxylic acid. It is weaker than the plus I effect, because this also is plus I effect. Na? It is weaker than the aliphatic carboxylic acid. Compared to this aliphatic carboxylic acid, the plus I effect is weaker. It is not minus I. Alright, it is plus I, because minus I had plus R, and as a result you will be getting the plus I effect. Due to this reason, you will find that the aromatic substituted carboxylic acid, alright, aromatic substituted carboxylic acid are somewhat stronger acid than aliphatic substituted carboxylic acid. Alright, that is, I mean to say that formic acid is always stronger, no doubt about it. After formic acid, you will be having benzoic acid. This is aromatic substituted carboxylic acid, which is greater than CH3COOH. You can see this is aliphatic substituted carboxylic acid. Alright, so this is stronger than benzoic, than what you can say, aliphatic. Alright, clear? So in this way we come to know about it. Fine. So acidic strength decreases in this manner. It decreases. Clear? Fine. Now next we'll see the effect of substituents on the acidic strength of aromatic acids. Now one thing is very clear, just like aliphatic, that if electron donor group is there, if ADG group ADG group means OH, CH3, OCH5, OCH3 group, NH2. This is attached to aromatic acids. It is going to decrease the acidic character. ADG group, very simple, just like your aliphatic. And EWG group. WG group means your halogens, your what you can say CN, CHO, COR, all multiple bonded. Alright, except halogens, which is not multiple bond, but halogens is considered under it because halogens has got high electronegativity. So what you find is that all EWG group will increase the acidic character. Alright, this you first need to understand it, that EDG group decreases the acidic character of aromatic carboxylic acid, and EWG group increases the acidic character. Alright, means H plus ion is readily released in case of EWG group when it is attached to it. EWG, again I repeat, it can be NO2 group, it can be CN, it can be CHO, it can be CO. Alright, so these are the group, we can say that. SO3H, these are the group, we can say. Alright, so they are the EWG group, which increases the acidic character of the aromatic carboxylic acid. So to say in other words, benzoic acid. Because here aromatic carboxylic acid is our benzoic acid. Alright, so it increases the acidic character of benzoic acid. EWG and EDG decreases the acidic character. This you understand it first. Done. Now, the acid weakening effect, alright, of electron releasing group, which is known as electron releasing means electron donor group, is more pronounced at para position than at meta position. You note it down this one. Alright, that is the acid weakening. I said, electron donor group decreases the acidic character. Alright, so the acid weakening effect is more pronounced at para position than at meta positions. Alright, that means I mean to say that if you are having benzoic acid, alright, and if you are having that is metabenzoic acid, which is stronger than parabenzoic acid, that is what I said, that in para position, see this is a acid weakening means electron donor group is there. So this para methyl benzoic acid is a weak acid compared to metamethyl benzoic acid, compared to benzoic acid. Benzoic acid definitely will be stronger because we don't have an electron donor group here. So definitely if no donor group is there, then definitely H plus ion is readily released. But here due to the presence of the donor group, the acidic character decreases. So acidic character is less at para position than at meta position. We can say that. Alright, the acidic character is less, so to say. Clear? This you need to understand it. Similarly, if electron withdrawing group is present, alright, electron donor we discussed. Suppose electron withdrawing group is present. Similarly, that is electron withdrawing group, that is if it is being present, same thing, it is more pronounced at para position than at meta position. That means I mean to say that para, let us say nitro group is there. Any particular group I have taken it, that is let us say nitro group. Benzoic acid, COH, and NO2 group is there. Alright, this is COOH. So it is para. This one is para nitrobenzoic acid. This, of course, you know meta, and this is your para. Alright, fine. So is more acidic. Alright, because I said that it is more pronounced at para positions. It is more acidic than what? Then meta. Is more acidic than meta. Alright, which is of course more acidic than simply COOH, benzoic acid. Alright, so same thing it is. The acid strengthening group. Alright, this is the acid weakening group, means this is your acid strengthening group. That is electron withdrawing group, we can say that, NO2 group is more pronounced, alright, in terms of carboxylic acid, aromatic carboxylic acid, at para position than at meta position, so to say. Clear? The reason is very simple. Para means stable. Stable due to symmetry. Stable due to symmetry. That's the reason. Got it? For that reason, acid weakening effect is more pronounced at para position. Acid strengthening effect is also more pronounced at para positions. Whatever it is, we can say that. Now, next is fine. So understood this particular thing. Next is ortho-substituted benzoic acid is always stronger then ordinary, what you can say, benzoic acid. Ordinary means which does not contain any other donor or withdrawing group. Alright, ortho substituted benzoic acid. Alright, ortho substituted benzoic acid is usually the strongest of all the acids. Alright, that is of the isomers of all the acid. Means I mean to say, suppose if you are having here, that is benzene ring COOH and it is CH3. This is ortho, in the ortho position. This is much more stronger than COOH. Much more stronger than COH. It does not contain any group, we can say that. Which will be much more stronger than what? That just now we studied. This will be much more stronger than what? It will be much more stronger than meta. COH, and this is your meta. What I have taken? CH3. And this will be much more stronger than nothing but para. Just now we studied that para group. Got it? Is if the acid weakening group is being present at the para position, it much more pronounced than meta. So you can see in this order. So generally it should be generally we think that, see here no donor group is there, so definitely this will be much more stronger, isn't it? No donor group is there, so H plus ion should be readily released. But here at least a donor group is there. At least a donor group is there, so acidic character is going to decrease compared to this. Think of and see. Here no donor group. So to the absence of donor group, what will happen is that H plus ion will be readily released. In all the case, donor group is there. Here also donor group is there. So H plus ion should be readily released in this case than this. Because donor group will decrease the acidic character. We have already studied. But why? Ortho is more than what you can say, this benzoic acid and this is meta and para. Meta and para are understood, that is. But the problem is why this is more than this. The reason should be this should be more than this. Answer is simple. The answer is due to the ortho effect. Ortho effect means it will suffer steric hindrance. Alright, it will suffer steric hindrance. The electron cloud of this and the electron cloud of this, when they will come closer to each other, they will undergo steric hindrance. Alright, due to the steric hindrance, what happens is that this will be more unstable in nature. As it will be more unstable in nature, so H plus ion is more readily released than this. Got my point? Here, this COH group and CH3 group, it is what you can say, the electron cloud are closer to each other. Closer means they will suffer steric hindrance. It will be unstable. And unstable means you know that it will release H plus ions readily. Unstable does not mean that this is not going to exist. Who said that? It is not going to exist. But the thing is that H plus ion will be readily released. For that particular purpose, that ortho benzoic acid is stronger than this. We can say that. This you need to understand. Alright? This is an exceptional case. And exceptional only comes in your exams. You might be knowing it. Similarly, if you have this is a donor group. If you have a withdrawing group like NO2, alright, if you have a withdrawing group like NO2, then what will happen? Here, this will be stronger, NO2. Then what is that? Then para. You have read it just now, that para, what you can say, nitrobenzoic acid, alright, is more stronger than, what is that? Meta, we can say it is more stronger than meta. So here I have to change it. What is that? NO2. And here it is nothing but simply benzoic acid. This is your para, this is ortho, and this your benzoic acid. Got it? So in this way, what we find is that this particular one, again the same thing, ortho nitro benzoic acid, more stronger than para, then meta, and then benzoic acid. We can say that because it does not contain any withdrawing group. We can say that at least a withdrawing group is being present. So this is an exception. Remember it. Got it? Now next is this is about your what you can say, benzoic acid. I talked to you, that is ortho, para, meta and all these things we have discussed. Next, I have already discussed with you that if you compare the acidic strength of alcohol and carboxylic acid, then carboxylic acid is more stronger than alcohol, because when H plus ion will be released in case of alcohol and in carboxylic acid, carboxylate ion is stable due to resonance. Carboxylate ion, that is RCOO minus, is stable due to resonance. So hence equilibrium is favored in forward direction. But in case of alcohol, that is ROH, what it will give? RO minus and H plus. RO minus is alkoxide ion. Alkoxide ion is not stable. It does not show resonance. So hence it is not stable. Due to which the equilibrium is favored in backward direction, and hence H plus ion is not readily released. H plus ion is not readily released in case of alcohol. due to which alcohol is less acidic in nature than carboxylic acid. Fine, this is very simple one. Now next is alcohol is much weaker acid than carboxylic acid. Rather, I should say carboxylic acid is stronger than alcohol, we can say that. So next is if you compare the acidic strength of phenol and carboxylic acid. Now this is quite interesting. Phenol and carboxylic acid. Now phenol also shows a resonance. Carboxylic acid also says resonance. Now you need to understand here certain things. Then you will be able to compare it. The acidic strength of phenol and carboxylic acid. Alright? So what is that? See here. RCOOH. Clear? So what it will be? That is what is studied here. This pair of electron will come here. Alright? And what I am going to get it? RCO minus, and here it will be what? It will be nothing but we can say that is or let me remove this because I need to compare the carboxylate only. So let me compare this only. So it will be what? This. We can say that. Clear? And here the carbon atom will be positive. We can say that. The carbon atom will be positive. Clear? So this particular one, it will be shown by the carboxylic acid. We can say that. Clear? So here we can say this goes here. So and this becomes negative, and here what you find is that oxygen is neutral, no doubt, and carbon becomes positive. Now if you want that the carbon should be neutral, then what I need to do? Then I have to go this. Got it? So due to this reason what happens? This becomes double bond. Now the carbon becomes neutral. Are you getting my point, all of you? Look here. You can do in that way, you can do in this way also. Either of that. So here one pair of electron will go. You will not have a pair of electron here. Alright. So in this way, what I find is that this particular carbon now neutral and oxygen is negative, and the negative charge is equally distributed in both the carbon atom, both the oxygen. Negative charge is equally distributed. So let me number it, this one 1 and 2. Alright, 1 and 2. So what you find is that here the negative charge is present. Listen carefully. Here the negative charge is present in the most electronegative atom in this particular group. The most electronegative atom is oxygen. So negative charge is present in oxygen, and the rules for resonance also says this, that the negative charge should be present in the most electronegative atom and the positive charge should be present in the most electropositive atom. So negative charge is present, and this negative charge is being equally distributed throughout these two oxygen. As a result, you will see it. If I draw the resonance hybrid, it is not required, just for your reference I am drawing it. If I draw the resonance hybrid, that is called as resonance hybrid, then what it will be? This will be this, and this I will be drawing a dotted line. This dotted line indicates what? That this is del minus and this is also del minus. That means this oxygen and this oxygen, let me write the del minus here. I hope you can see it. The del minus here and the del minus here. So the negative charge is equally distributed between these two oxygen atoms. So negative charge is delocalized. That means energy is distributed. It is delocalized. This is, I have drawn the resonance hybrid. It is not required here to explain, but just to explain you that how the negative charge is distributed, I have done this. Alright. So these two are the lone pair of electrons you can see in oxygen. These two are the lone pair, and this double bond is equally distributed between the two oxygen atoms. Double bond means what? The electrons is equally distributed, and hence we get this is called as a resonance hybrid. This is known as resonant hybrid, and you must be knowing this is known as canonical structure. These two structures are the canonical. This does not exist. You have read it in resonance. This actually exists. This exists only in pen and paper. This is theoretical, but this is practical. Practical means we know that yes, in case of carboxylate ion, what you find that one oxygen is negative, other is not positive. Both the oxygen are equally negative because charges are equally distributed. For that reason, you will find the bond length is also being same between this carbon oxygen and this carbon oxygen. The bond length is also same. We have read all these things in resonance. In class 11 you have studied. Fine. Just to explain, I said it. Now let me come to, that is phenoxide ion. This I said you the carboxylate ion. This is your carboxylate ion I have discussed with you. Now I am going to discuss with you the phenoxide ion, so to say. The phenoxide ion. Here the negative charge is there. That is initially, that is the negative charge is there. Alright, initially the negative charge is there. Sorry, I forgot to write the negative charge here. So hence, now you can see that. That is the phenoxide ion, we can say. Now carboxylate ion. Now I am come to the phenoxide ion. Phenoxide. So phenoxide, you can see this one. What is that? That is nothing but phenol, na? O minus. See. So what will happen? A pair of electron will come here. Let me number is that 3. This particular one. So let me number it at 3. So here what will happen? The canonical structure, if you draw the canonical structure, it will be double bond, this. Alright, fine. And we got this particular one. This number is, let me as 4. Alright, this I am taking it as 4, this particular structure as. Fine. Now, after that, what will happen is that this pair of electron is going to come outside. Now, it is very interesting. So, this becomes negative. Again, this will come outside and this becomes. Here it comes, here it is, and this goes here. Now, this comes here. Alright, this comes here. So, the structure will be here, that is, I don't have the space here, I am drawing it still then. So you can see here it is and here it is, of course this is there, and this particular one comes here. Alright, so it is 4, 5, 6 and this is your 7. Now in 1 and 2, basically, because this I don't need, this is resonance hybrid, I don't require. Just for your reference I said you. If you see 1 and 2, then the negative charges is equally distributed, you can see that. It is being dispersed. Alright, it is dispersed and it is present in the more electronegative oxygen atom. It is more stable, for that reason it is more stable due to resonance. Here the negative charges is localized, you can see, here the negative charge is localized. Negative charges, it is not delocalized. And the negative charge is present here, listen carefully, the negative charge is present here on the less electronegative carbon atom. You can see this is carbon atom, this is carbon atom, this is carbon atom. It is present on the less electronegative compared to oxygen and carbon, which is more electronegative, oxygen. But it is present, negative charge is present on the less electronegative carbon atom. So hence it is less stable in nature for that particular purpose. What is less stable? Phenoxide ion is less stable compared to carboxylate ion. Alright? The negative charge here, it is first of all localized, as you can see it here. It is localized on the oxygen atom. But when it is delocalized, it is being delocalized on the less electronegative carbon atom. Alright, it should be on the more electronegative carbon atom according to the rules of resonance. The negative charge should be, as you can see it here. So this is more stable. Here the energy is more distributed. Alright. Here the, what you can say, the negative charge is much more delocalized. Here the negative charge is delocalized but on the less electronegative carbon atom. Less electronegative carbon atom. Due to this reason, phenoxide ion is less stable in nature compared to carboxylate ion. As it is less stable, the H plus ion is not readily released in case of phenol compared to carboxylic acid. So it's a comparable term, relative term it is. So I need to compare it because I am going to compare I am comparing this one. So hence carboxylic acid is a much stronger acid compared to phenol, so to say. Clear? Understood this? So here we come to, that is the comparison between carboxylic acid and alcohol, between carboxylic acid and phenol. So ultimately we concluded carboxylic acid is more acidic than phenol, which is more acidic than alcohol. We can say that. Understood? Thank you.